generalizing the learned contact-rich manipulation skills toward object textures and Sim2Real domain gaps is imperative for robotic chemists. There are three main challenges. First, detect in-hand transparent objects using vision only is difficult in contact-rich chemical experiments. Second, positional uncertainty in robotic grasping as well as variations in tubular objects being manipulated indicates unseen in contact surfaces. Finally, brittle optical tactile sensors and costly real-world training require learning tactile motor policy via Sim2Real transfer. We propose a method for learning robotic skills of tubular object manipulation that are generalizable toward object textures and Sim2Real domain gaps. This is achieved via decoupling RL-based skills and pixel-level tactile image transfer, which includes a pixel-level unsupervised domain adaptation network that cascades CNNs and transformer (CTF) cyclegon, and an object in-hand pose estimation network (AngleNet). The proposed method ensures high generalization capability of in-hand pose estimation toward unseen surface texture of the tubular objects. We train the proposed method and RL-based policies in the simulator, and the method is implemented for learning Sim2Real transferable robotic insert and pull-out actions, which is further applied to a human-robot collaborative tube placing scenario and a robotic pipetting scenario for a robot chemist. We transfer tactile images using proposed CTF cyclegon. As shown in the table, CTF cyclegon has a significant improvement in the FID, KID and SSIM indicators in the Sim2Real pipeline compared with other methods. And compared with cyclegon, our method generates tactile images with higher quality, as shown in the figure. For estimating the deflection angle, we design an object in-hand pose estimation network, AngleNet. The table shows the quantitative accuracy evaluation results of AngleNet, which demonstrate the model's capacity for generalization. In this work, we build a RL-based robot manipulation skill learning platform using MuJoCo and modify from GelSite simulator to Digit simulator. To learn the robotic tactile-based insert and pull-out tasks, we choose SAC algorithm. And the right figures show the reward and success rate curves in the training process. Finally, we evaluate in two real-world scenarios: human-robot collaborative tube placing and robotic pipetting. The left video shows 3 continuous tube placing episodes. We can see that a human participant passes the test tube to the robot, and the robot holds the tube at the bottleneck, the side, and the cap, respectively. The tube's deflection angle θz in the initial position is different every time, and the robot adjusts the gripper pose to make θz gradually approaches 0 degree by learned policies, until the insert task is completed. In this video, the first 2 tubes belong to the tubular objects with seen texture, and the last one belongs to the tubular objects with unseen texture. The right video shows 2 continuous robotic pipetting episodes. We can see that the robot conducts the 4 steps of reach and insert, suck up, pull out and reach, and squeeze out in sequence to transfer reagent from a vial to a beaker. The dropper's tip is constantly held by the robot's gripper. And the dropper belongs to the tubular objects with unseen texture. The left figure shows the error bars of the deflection angle we recorded in experiments. And the right table shows the success rates of 2 scenarios, which demonstrates the generalization capability of the learned tactile motor policy toward domain gaps as well as unseen in-contact texture. To sum up, we propose a skill generalization method for robotic tubular object manipulation tasks. In particular, we present a novel Sim2Real transferable in-hand pose estimation method using unsupervised adversarial domain adaptation of tactile images. Using the in-hand tubular object pose estimation results, the RL-based object insert and pull-out policies learned in a simulator generalizes well to unseen real-world in-contact object texture, as well as the Sim2Real domain gaps of the tactile sensor. The proposed method is further evaluated in a human-robot collaborative tube placing scenario and a robotic pipetting for reagent transfer scenario. Thank you for your attention.